Okay, we are continuing on here. I don't know. Chapter 19. That sounds like a good one. Why not? So last time we talked about transition metals, a little bit of background. And we also finished talking about, or started talking about coordination compounds. And really, coordination compounds are made up of two things: a complex ion and a counter ion. And as we talked about, the complex ion can be positive overall, and the counter ion would be negative. You can kind of think of them as like ionic sort of compounds. We could also have a negative complex ion and a positive counter ion. They do go much like an ionic compound. It's always the positive guy first, followed by the negative guy. And what a complex ion basically is we have a metal, a lot of times a transition metal or a metal with a good positive sort of charge, and we have a number of ligands that are attached to it. And remember that ligands are Lewis bases, and those are things that will donate a pair of electrons. Um, So things that are really good Lewis bases are things that a lot of times are polar. They have some non-bonding electrons. Are there negatively charged ions? Because they obviously are negatively charged. They have some extra electrons to sort of give. So like our water, for example, is a good ligand. It's polar. It's got those pair of electrons to give. Remember that ligands can be what are sometimes referred to as being monodentate. Which means they basically bind in one place. We could also have some that are bidentate that bind in two places. And the two really common ones you come across a lot are EN, which is very often abbreviated as EN, which is ethyl endyl diamine. And that is this guy that looks something like this. And each of the nitrogens can attach to the metal. So again, you get kind of like a 2-for-1 sort of situation happening when you have one of those guys. Also, oxalate is another very common sort of bidentate one that you come across. Oxalate looking something like this, perhaps. And same thing, it's actually those single bonded oxygens that will bind to the metal and give you kind of a 2-for-1. There's some that are referred to as being polydentate that can bind in multiple places per molecule. So for example, EDTA, I think we saw at the end there, could bind at 6 different places per molecule. This makes a difference when we talk about coordination number. When we talk about coordination number, that is how many atoms are attached directly to the metal. So sometimes when people see formulas, they sometimes think that that is always going to be sort of the coordination number. So for like the one we looked at this morning, we had this guy, I think, something like this. And the ammonia here is our ligand, and ammonia is a monodentate ligand, which means there's really 4 of those ammonias attached to the copper. And that means that the coordination number here would be 4 in this case, as when the ammonia attaches, only the nitrogen here that has the lone pair is going to attach to the metal. So you get a 1-for-1 sort of situation in this case. So the coordination number here would be 4. Now, if we had a different ligand, like we had our oxalate, for example. So if we had our same guy there, we had something like CuC2O4 2 minus 2 overall. When we look at this oxalate, some people will say the coordination number is 2, but because each of those can bind twice per molecule, we would have another oxalate hanging out perhaps over here. where each of those oxygens would also bind, which would give us actually 4 for the coordination number, as it is basically a bidentate. So it's not always going to be the subscript in the formula. It will be equal to the subscript in the formula if it's, again, a monodentate ligands that you have, or if you have all monodentate ligands, you could add them all up. But if you do have some bidentate or something like that, you do have to sort of adjust the coordination number. Any questions on that stuff there? All right. So how many ligands do we typically get to sort of bind in? It does sort of depend usually on the charge. So as you can see, something with a +1 charge, as you can see here, very common coordination numbers are 2 and 4. So you'll get 2 or 4 sort of ligands coming in. As you get a little larger of a positive charge, you can start getting to your 4s and 6s, and even positive of a charge, if that's a word there, will get you a coordination number of 6, except for gold here. We'll kind of hang out with a coordination number of 4. So again, the sort of larger the positive charge, remember, we could kind of look at complex ions as Lewis acid and bases. So the higher the positive charge on the metal, the more electron deficient it is, which means it's actually a pretty good Lewis acid. And that's going to allow more of those electrons to be able to bind into it. So here, I guess I drew it right, so that's good. So that is our ethylenediamine. And once again, it is very commonly both in formulas and also names used as EN. And again, it can bind through those two. This big guy right here is our EDTA, and it can bind through a metal through there, and there. That is 6 places per molecule. It has the ability to bind in, and that's why it's a really good, as it says down there, chelating agent. A chelating agent is something that basically can tie up a metal pretty good. So just one of those will ultimately surround that metal pretty tightly and keep it pretty contained within it. So here's a table. You have a similar one in your book of some of the monodentate or unidentate ligands. Again, all these guys up here is going to give you kind of a 1 bond per molecule. Here's our 2 common bidentates, our ethylenediamine and our oxalate, which is going to give you kind of a 2 per molecule. This is diene, which actually has 3 nitrogens here that can bind. So this guy actually will give you 3 per molecule. And this is our ethylenediamine, which, as you can see right there, ethylenediamine tetraacetate, or sometimes called acetic acid. That'll be the bonus question to spell that, I suppose, right there. Like, never mind. I don't want to do it. Wow. I'm just going to zoom in again so you can see it again. All right. Also has a, as you see there, -1, -2, -3, -4 charge overall happening in that case. All right, and then you got to spell it backwards. So, all right. So as you can see here, here's a sort of 3D structure there of our EDTA. And as I mentioned, I think last time, it's used a lot in a lot of products to really sort of trap metals and stuff like that. You sometimes can even see it on a lot of ingredient labels. Sometimes EDTA is used in it. So what is the oxidation numbers of the metals in the complex ion part? By the way, typically when they are written as coordination compounds, when you see a little bracket, that is the complex ion part. So why don't you take a second for the metal in the complex ion? What is the oxidation state there? Okay, so let's take a look. So once again, when you see this sort of written, this part that's in the bracket is typically your complex ion. That means that this guy here would actually be our counter ion. And if we take a look at it here, we got OH, which is OH minus, right? So that's -1 for that guy. There's 4 of them, which gives us a -4. And our potassium is just a potassium ion, right? Which is +1. So Obviously, this overall thing has no charge, so we're looking at a +3 as our oxidation state there for our actual metal that's in there, polyatomic, or complex ion in this case. Question on that there. If we look at the next one here, we got CrNH36. NO33. All right, so when we look at this particular one here, we'll start out over here. Ammonia is 0, right? No charge. So though there's 6 of them, it's still 0. This is nitrate hanging out over here, so that's -1, and there's 3 of them, which gives you a -3. So in this case, to balance it out, that's going to be +3 in this case for the chromium. Once again, this would be our complex ion in this case. And this guy here would be our counter ion. First up, any questions on assigning the oxidation states? Now, if we were to look at this, we actually do see both of the situations that we talked about earlier. When we look at just the complex ion part, for example, of our first one here, the charge on just the complex ion part is going to be overall, what's the charge on just the complex ion part? It is going to be -1. Once again, that is -4, -1, and there are 4 of them, which gives you -4. We just determined that this gold has a +3 charge, which means overall our complex ion here is actually negative with a -1 charge. That is why we have just one counter ion, right, which is positively charged. So just like an ionic compound equals to 0, positive guy, then negative guy here. And that is what we got going on in this case. Now, different over here on our second one, when we look at what's happening here with our complex ion part, we know that this is +3. And as we just talked about, that is 0, which means overall here, our complex ion really is carrying a +3 charge, and it's actually a positive complex ion in this case. That is why we need not 1 nitrate, not 2 nitrates, but we need 3 nitrates, right, to give us a -3 charge to balance out the complex ion's charge. So in this case, our complex ion is actually positive, our counter ion is negative. So much like an ionic compound, as we talked about, it's always the positive guy first. So that's why in this case, we went with the counter ion first, and then our negative complex ion. And here we went with our positive complex ion, followed by our negative counter ion. Any questions on any of that there? Okay. So this is really important. Sometimes you do want to sort of figure out, is your complex ion positive or negative? And really, if you have it written like this form here, you could actually just tell by where the complex ion is in the formula. So obviously on the first one, second comes second with the brackets. Second one there comes first, so you know it's positive in the second one and negative in the first one. And that helps for the naming aspect of it, which is, let us talk about naming these fun things here. So let's talk about all these fun rules about naming coordination compounds and really also naming complex ions. So the cation is named first before the anion within the complex ion part of the name. So within the complex ion part of the name, and remember in a coordination compound, there could be 2 parts to the name. There'll be the counter ion and the complex ion part. So when you're talking about just the complex ion part of the name, the ligands are listed first in alphabetical order, regardless of any type of prefix that you may have. So what I mean by that is maybe you have 2 of the same ligand. So maybe you use the prefix di. So you would ignore the di part of it and just go with the ligand's first letter in terms of alphabetical order. Now, the metal is always named last in the complex ion part of the name. So that does not mean that the metal is always named last in the entire name, but whichever part of the name is the complex ion part should have the metal coming there at the end. Names of negatively charged ligands usually will end in the letter O. Some neutral ones are usually just called the name of the molecule. There are some exceptions. Water is known as aqua. Some people call it aqua. Carbonyl there for CO. Ammonia is amine. If you do have several the same ligands in a particular complex ion, you will use some prefixes like di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, to indicate how many you have. If the ligand already itself has a prefix in the name, then you will roll to some other prefixes like bis, tris, bis for 2, tris for 3, tetrakis there for 4. Could be making this up, but I'm not. But so you would roll with these prefixes here. So what do I mean by that? If we take a look at our EN, which is a very common one you'll come across, that is known as ethyl endyl diamine. So it has the di in the actual name of it itself. So in that case, you would not use di again. You would use bis or something like that in that particular case. So if the ligand itself has some type of prefix in it, you roll with these other ones. Lastly, the oxidation number for the metal in the complex ion is always written in Roman numerals that come after the metal's name. And unlike some things that we do with normal nomenclature, for example, things that have fixed charges that are transition metals like zinc and silver, right? We typically do not put Roman numerals with those. When you're doing this type of naming, you actually do include the Roman numerals. So things like silver, you would still put 1, zinc, you would put plus, we put Roman numeral 2. So pretty much you're always going to put a Roman numeral in there for the charge on the metal, regardless if it's sort of like a fixed charge or not. You will always sort of do that with this. You will also sometimes, as odd as this may sound, put a 0 if the oxidation state of the metal is actually 0, which can happen oddly enough. So you will actually put a 0 there for it, and you can end up, once you kind of go through all the oxidation states of everybody, you can end up with a metal that actually has no charge on it and stuff like that. So it's kind of weird, but you can sort of end up with that in this situation. Lastly, if the complex ion part is negative, you're going to roll with the old school name that ends in -ate. So instead of iron, it'll be like ferrate. Instead of copper, it'll be cuprate, plumate for lead, and so forth. If the complex ion is positive, you'll just roll with the regular name like iron, copper, and stuff like that. Good times. I have no idea who made up these names. I do. So let's take a look at some of these ligands, and we'll see how to put this to use here in just a second. But here's a table. Like I said, in your book, you have a similar sort of table. So water is aqua or aquo, amine, methylamine, carbonyl. Our sort of halogens are named very similar to what you do in organic chemistry. So fluoro, chloral, bromo, iodo, hydroxo for hydroxides, cyano there for a little cyanide. Here's some of those old school names that you would use if the complex ion is negative. So ferrate, cuprate, plumate, argentate, arurate, and stannate there for tin. Here's some of the other ones. You got some hydroxo, you got some carbonato, a little oxalato. It's almost like I'm ordering a drink, but I can't use my points, so I will not order it. I would like oxalato, carbonato, bente. I don't know the size. And there's our ethyl endyl diamine. So again, if you were to use this guy and you had multiples of it, because it does contain that prefix, you would not use the regular prefix. That would be where you would use something like bis or tris. I will also say for oxalato here or oxalate, sometimes people will also use the bis, the tris, because it's a bidentate sort of ligand. But for us, you could use the regular prefixes. Here's our other, that's EDTA over here. Ethyl endyl tetraceto. There we go. So you could go with that one as well. So let's see how this sort of works. Let's just take the ones that maybe we did previously. Which ones did we do previously? Or you just looked at there. All right, so let's say we wanted to name these guys. We would start with the first one here. Since we already determined that this is our counter ion and this is our complex ion, we would start with the counter ion. And the good news about counter ions, regardless if it is positive or if it's negative, you basically just use the name of it, right? So just like if we had K2O, you would call that potassium oxide, right? Regardless of how many potassiums you have, you just basically use the whole name there of the counter ion. Now here we have some ligands, which in this case, I feel like my parentheses is in the wrong spot there. We do have hydroxide there, so we would want to go to our table and figure out again what we should call it in. As we know here, I think it was right here, maybe there it is. Hydroxide is going to be hydroxo, and that is what we're going to use. So so we have 4 of them. So that's going to be a little tetrahydroxo. And now this is going to be gold, but this is a negative complex ion, which means we cannot use gold. We do have to use our sort of old school name for gold, which if we look over here, I think we saw it right about there. So we would want to use aurate here. And that would then put that together here. Roll this way. That's a little aurate, Roman numeral 3, right? So this is the complex ion part of the name. That is the counter ion. So that's a little potassium tetrahydroxo aurate 3. Yes. It is, yeah. So regardless of how many you have, it'll just pretty much end up being just pretty much the name of it. Well, I don't know. I don't know how to answer that yet, but perhaps would be good. Yes. I don't know, be on the final, I suppose, at some point, I suppose. So I'm going to say temporarily, yes. Maybe a good idea to have some familiarity with it. Yes. All right. So that is potassium tetrahydroxo aurate 3. By the way, if we just had the complex ion part, that is going to be pretty much just this last part. It's just going to be tetrahydroxo aurate Roman numeral 3, and just put ion at the end of it there. Question on that fun name there. It's a nice size name, I think. All right, so why don't you give a go with this guy? Why don't you name this guy here? See what you got going on. So I just put it here, maybe. So we had chromium NH3 6, I think. Okay, so let's take a look. So we earlier established that obviously our complex ion here is coming first, which means it's a positive complex ion, and we have a negative counter ion, which is the nitrate in this case. Because it's positive, that you can actually just use the regular name for the metal, so we don't have to use the one that ends in ATE. We do have 6 of these ammonias, and again, that's going to be amine. Prefix for 6 is hexa. Amine. This is then going to be our metal, which should come at the end of the name here of the complex ion. Chromium, Roman numeral 3. And once again, here our counter ion, even though we got 3 of them, will just be called nitrate. So that would be hexamine, chromium 3, nitrate. Yeah. Questions on that name? By the way, the coordination number here would be, it would be 6 for the complex ion, right? As we have 6 monodentates. Coordination number for the previous one we did would be 4 again. Hydroxide there is also monodentate, so the coordination number here would be 4. Question on that there. So this also illustrates what I was saying earlier. When we talk about the metal coming at the end of the name, we're talking about the complex ion part of the name. So this is really the complex ion part of the name. So that's why it comes at the end, not necessarily the end of the actual name of the compound. All right. Fun with naming. You thought it was over, right? So let's take a look at this one here. I think on yours you got some water maybe hanging out there. Yeah, we'll hydrate to further complicate it. But if we look at this here, we got a couple of things happening. It disappears and then it comes back. Maybe there we go. We have definitely our complex ion part here. The charge on the chromium in this case would be, this is oxalate, which is -2. And there's 3 of them, which means -6. There are 3 potassiums, which would give us a +3. So +3 and -6 means that the chromium here would be +3 to balance it out, right? Coordination number, by the way, for this one is? It is 6. So this oxalate is a bidentate, which means for every 1 oxalate molecule that you have, both of those oxygens are going to attach to the metal. So you get kind of a 2 for 1 on that deal. So again, here, the coordination number actually would be 6 in this case. We also can see that our complex ion actually comes second, which means it's negative. So we're going to have to use actually the ATE version of chromium, which is like chromate. Once again here, this is our counter ion, which is our potassium. So in this case, we once again will just use the whole name of our counter ion, which is potassium. We then would have 3 oxalates, right? And again, our oxalate has the oxalato type of name there. So we're going to go with trioxalato. And here, put the thing back so I can see it. That would be good. And now we will go with chromate, ATE, as that guy is negative. And once again here, Roman numeral 3. As I mentioned earlier, oxalato, because it really is bidentate, sometimes they will also use bis in there as well for this particular one. So you sometimes will see as bis oxalato chromate 3. And by the way, this would be without the water, what I just wrote there. It would be that. With the water, waters that are attached with a dot are known as hydrates, right? And that would then be a little trihydrate, means 3 waters, right? And you could add that to the rest of it there. Question on either of those names? Yeah. No, it's actually 6 just from the oxalate. So for example, here, if we have the chromium in the middle, we just look at the complex ion part. If we drew one of the oxalates, which looks like this, and this one oxalate will bind at 2 places per molecule. So if we had another one, let's draw it this way. This second oxalate molecule would bind like that. And lastly, if we had a third one, it would bind like that. And that would give you your 1, 2, 3, 4, 5, and 6 molecules that would be bound there, which would be your 6 coordination numbers. Right. So it's not always going to be the number. It will equal the number if it's a monodentate ligand. But it is sometimes bidentate like this, so you'll get a 2 for 1 sort of deal. Other questions on that there? All right. So why don't you give the name and the formula here for this particular one and see what you come up with. Okay, so let's take a look and see how you're doing. We got our complex ion part here. That means the Cl here is our counter ion in this particular case. So probably the first thing you want to do is maybe figure out what is the oxidation state or charge on the metal and the complex ion. Water is 0, I hope still. That is -1 for the Cls. There's 2 of them, gives me -2. I also got a counter ion on the outside that's -1. that means that the chromium here is carrying a +3 charge or oxidation state. Coordination number of this guy is? It is 6 in this case, yeah. So the coordination number here would be, this is a ligand and those are ligands. They're each monodentate. Coordination number here would be 6. You basically have chromium in the middle, 4 waters attached to it, and 2 Cls basically attached to it, right? So that gives you a coordination number here of 6. We could also see from the arrangement here that our complex ion is going to be positive as it comes first in the formula, which means we could use the regular name for chromium. So we have 4 waters, so prefix for 4 is tetra, and you can use aqua, whichever one you like. We have 2 Cls, which the prefix for 2 is di, and a little chloral action. And then we have a little chromium, Roman numeral 3 happening there. So that's the complex ion components. We need to put it together in alphabetical order, which means which one comes first? Yeah, we are going to ignore the prefixes and look at the actual letters there. So this would be something like tetra, aqua, dichloral, chromium 3. And my counter ion is also a Cl, which would then be called chloride, just like we would in an ionic compound. Yeah. So, that just rolls off the tongue there. A little tetra, aqua, dichloral, chromium 3 chloride. Also known as that thing when people point to it and go, they ask a question in lab manuals like, what's that thing? This question on that. Obviously, if the counter ion was not there, our complex ion would have a -1 charge and a +1 charge, I'm sorry. And we would name it the whole entire way there, except replace chloride with ion at the end, right? Now we want to write the formula here for this particular guy. We have tris, which is 3, and that's that secondary prefix. And the reason we do need to use it is because, again, in the actual name of the ligand here, there is a prefix in there, which is di. So that is why we're using tris in this case. Ethylenediamine is our friend En, basically. So we basically have 3 of these guys. We also have a cobalt that has a +2 charge, and that's really our complex ion part. And I know my complex ion part ends there because when you name it, the metal should come at the end of the complex ion part of the name. So that clearly is the complex ion. So putting this together, if I just put this as my complex ion, it would have a overall +2 charge, right? Because En is neutral. And that's important because my counter ion in this case is sulfate, which has a -2 charge. That means I just need one of those to balance it out. And that means that the actual formula would be COEN3 SO4. As the -2 here will balance out the +2 there in our complex ion. Question on either of those there. Coordination number on that guy is? It is 6 as well. Once again, this is bidentate, which means you get a 2-for-1 situation there. So all 3 of those will give you 6 attachment points basically to that metal. Question on those there. All right, let's continue the fun here, shall we? Here we go. Give the name for each of these. Yeah, let's take a looky here and see. Once again, we can see by the bracketing here, we got our complex ion here. Our Cl going to be our counter ion. Also tells us our complex ion is going to be positive. Looking at the oxidation state there, we got 0 for our ammonia. That's going to be -1 for our chloride there. That's going to be -1, and there's 2 of them, which gives us a -2. So overall negative we got going on here is 3. So in this case, we got a +3 happening here for our cobalt. Also, coordination number of this guy would still be 6. got 5 ammonias and 1 chloride attached to it, right? And they're all monodentate, so that'll give you 6 total. Here we raise a roll. We got 5, which is pentamine. We got just a chloral happening. And we have a whole name, regular name there, cobalt-3 happening. So alphabetical, I kind of do have an alphabetical there. I guess we'll just go that way. So we'll go with pentamine, chloral, cobalt-3. And once again, our counter ion here is going to be our chloride, and it gets the normal, since it's negative IDE ending. Obviously, if it's a polyatomic ion like the one we had previously, it would just be the polyatomic ion's name. Question on that one there. Coming here, we see our complex ion here and our counter here. That means that we have a negative complex ion in this case, which means for our iron, we got to roll with a little ferrate action, right? Our counter ion, which is potassium group 1, is +1. There's 3 of them. Cyanide is -1, and there's 6 of them. So to balance that out, in this case, our iron will be carrying a +3 charge. Coordination number here will also be 6 in this case. Won't always be 6, but in this case it will be because we have 6 monodentate guys attaching. So we know that's going to be a ferrate 3 happening there at the end of the name. Once again, here we'll just start with our counter ion. So it's going to be potassium, regardless of how many you have. We will go with hexacyano for our cyanide, and 6 of them being hexa. And finishing with our metal name there and Roman numeral at the end, a little potassium hexacyanoferrate 3 happening. Yeah. Question on either of those names there. All right, so let's try a couple more here. Let's do some formulas next and see what you come up with. All right, so write the formulas for triamine bromo platinum 2 chloride and a little potassium hexafluoryl cobaltate 3. You could do it either way. You could write the formula for it for the ethyl endylamine if you want. Most people will kind of use the abbreviation for it when you're doing kind of complex ions, rather than writing the formula for both the formula and also the name. They'll use that abbreviation. But if you want to write, CH2, NH2, and all that, you can if you want. Yeah.
It was just like a little memory flex. I never learned it that way.
No Chem they will use the other way, but for these complex ions, sort of non-home chemish, if you will, they will kind of use that abbreviation for it. So they also kind of write it all out. Okay, so let's see what we got here to build. So we got a little triamine. So right there, tri is 3 and amine is ammonia. So we got 3 of those. We have a bromol, which is a Br, and we have a platinum that has a +2 charge. So once again, up until this point is our complex ion. And I know that because at the end of it is the metal's name. So that's where it ends. So we do want to kind of put this together really here. So our complex ion part will look something like this. And a Br. And if we just think about sort of what the overall charge here is, that'll be +2, that would be 0, that would be -1, which means we really have a +1 overall charge for our complex ion part of it. And once again, figuring that out is also important for your counter ion here. So you know how many you need. So in this case, since it's just +1, we just need 1 of the Cl minuses to balance it out, which means our actual guy will look something like this, I think. Any questions on that there? Yeah. So I would say typically when you write the complex ion part, a lot of times they'll start with the metal, and then they'll kind of do the ligands, like sort of like in the name in alphabetical order. Is it technically wrong? Not really, because it's all together there, but that's just sort of commonly how it's done. It's kind of the metal first in the formula, followed by the ligands and stuff like that. Other questions? Okay, so looking at this one here, I got potassium, and then I got a little hexafluorocobaltate 3. So clearly this part here where it has the metal and the Roman numeral is our complex ion part, which obviously tells us it's negative because we see the 8. And this is going to be our counter ion here. So we can start with the counter ion, which is K+, and then hexafluoral means I got 6 fluorines. And cobaltate is cobalt with a +3 charge. That means if I were just to put together my complex ion part, it will look something like this. And since each of these are -1, that's -6, and this guy is +3, which means my complex ion is rocking there a -3 charge that's happening in that case. That means in this situation here, we will need 3 of these guys to balance it out. So we'll need something like this, perhaps. Yeah. Question on that there. Question on naming and writing these formulas, which you might need to know how to do for the final. Just going to be all these nonstop every page. It's a bunch of blank scratch paper to write the giant name as you write it all. Any questions on any of that there? All right. All right, so continuing on here, let's talk a little bit about isomers. Isomers are typically things that have kind of the same formula, but a lot of times they do vary in sort of how they are connected. There's some different sort of classes of isomers or structural isomers, which have different bonds, and some of those are, in this case, coordination isomers and linkage isomers. There's also stereoisomers, which have the same bonds, but different sort of spatial arrangement in 3-dimensional space, and that gives you geometric isomers, which sometimes are referred to as cis or trans isomers, and optical isomers, which can sort of rotate plane polarized light. So we'll take a look at some. First off, we'll take a look at coordination isomers. So here's our 2 coordination compounds, and that is our complex ion part. And obviously in this case, each of these are our counter ions. Now, in the first case, and if you just sort of count everything, if you will, if you count everything, they both have pretty much the same number of chromiums, the same number of NH3s, the same number of sulfates, and the same number of bromines. So they're isomers. They basically have the exact same guys arranged. The difference, though, is in the first case, the sulfate is actually attached to the chromium. So we would have our 5 ammonias attached, and also our sulfate in this case. And our counter ion in this case, I'm assuming that's going to give us a +1, is our bromine that's hanging out there. In the second one, although they're all just still the same stuff here, the difference is in this case, is still our 5 NH3s. But we actually have bromine directly attached there, which would give us a +2 overall charge. And our sulfate in this case is the counter ion. So these are what are referred to as coordination isomers. They differ by really, what's the sort of counter ion and what's attached to the complex ion in this particular case. Any questions on that there? Another type of isomer is a linkage isomer, and a linkage isomer also, again, will have pretty much the same elements and guys involved, but actually upon the ligand itself, it could actually attach to the metal using different elements within it. So if we look at NO2 minus here, NO2 minus could attach through the nitrogen, or it could attach through an oxygen in this case. And that's what we see here in our cobalt. In the first case here, the same ligand is attaching through its lone pairs there on the nitrogen, while here in the second one, it is attaching through the lone pairs of the oxygen in this case. So this is what is referred to as a linkage isomer. You basically have the same ligand, but different elements within that ligand can attach. In each case, they're still attaching monodentate-like. They're only attaching through the nitrogen or the oxygen in this case. So it'd still be more of a monodentate attachment that's happening, but it has the option of using either the nitrogen or the oxygen in this case. And that obviously creates some different sort of properties based on sort of how it bonds into there. Question on the difference between linkage and coordination isomers. Now, stereoisomers are sometimes referred to as geometric isomers, and that requires sometimes cis or trans. And when we talk about cis and trans in organic chemistry, we talk about cis and trans a lot of times with a double bond. And it means, for example, you have the same group on the same side of the double bond is known as cis, and you have trans on opposite sides here of the double bond. So it kind of means the same thing here. Cis is basically the same side, and trans is the opposite sides. And what we're talking about here is sort of the plane of the molecule, as there's kind of really no double bond happening in these particular compounds here. So either they're sort of on the same side of the plane of the molecule, or they're on opposite ends. They have the same atoms, they have the exact same bonds, but they do have different bond angles. Very common in square planar complexes. Remember, square planar is the one that looks like a square. Yes, a little exception. It's within the plane. I was going to not say it, but I said it. Right. So that's the expanded octet. Yeah, square planar. Little 6 electron pairs, 4 bonds, I think. All right, looks something like that. So here's our square planar happening here, and here we have the cis isomer, and you can really look at either one of these. They're on the same side, basically, of the plane. Either of those groups are the same. And we have the trans, which, say, if you want to look at the chlorines, you could. They're on opposite sides, or even the ammonia here. You could look at each of those, and they're on opposite sides of each other. So that's our cis and our trans. They do give a little bit slightly different sort of properties depending on how they sort of hook up, but they basically have, again, all the exact same bonds happening there. Here's a octahedral sort of arrangement. If you remember octahedral, 6 electron pairs, 6 bonds. Yeah. We got trans here on our first one, and here looking at the chlorine, one is sort of above the plane, if you want to think about this as being your plane, and one below the plane of the molecule, maybe a little easier to kind of see there. Here, they're kind of on the same sort of side of the plane. We got one on the main plane and one above, which kind of puts them on the same orientation, and that would be our cis in this case. And again, you'll have some different properties depending on sort of which one it is, our cis or a trans. Now, optical isomers are isomers that have opposite effect on plane polarized light. Molecules that have a non-superimposable mirror image are what are referred to as being chiral. And these isomers are sometimes referred to as being enantiomers. Chiral molecules are things that if you stick it against a mirror, so if you stick something here and you see the reflection and then you take the reflection out, that means that you cannot basically superimpose the reflection in the mirror exactly on the original molecule. So the most common sort of example of chiral are your hands. You have this hand and you put it in the mirror, you get this hand. Yes. Nice. And if you pull out the mirror image from the mirror, you can do as much as you want. Don't break your hands if you try. You'll never be able to superimpose them correctly, right? I got thumbs on the right side, but I'm palm up, palm down, so that's not right, right? If I flip it this way, palms are good, thumbs are on the wrong side. So no matter how you rotate your mirror image, Again, don't injure yourself if you try yourself. You will never be able to get the mirror image to fit perfectly on top of the other. So unpolarized light consists of waves vibrating in different planes. And when you do have these sort of chiral guys, there's your hand example there, where you can pull it out and rotate. They will be able to rotate it, and you can also measure the angle at which they kind of rotate that light as well. So if we look at a object like this, and sometimes it's hard to visualize when you're looking at it, but if we kind of super zoom in here, here we have mirror images. And if this was the mirror, obviously it's going to reflect there and reflect and reflect. And in this case, when we do pull this one out here, they cannot be superimposed on each other. And you may look at it and go, it looks like they are the same sort of molecule. But the real difference where it really messes it up no matter what you do is actually when this guy gets sort of mirror imaged here. In the original connection, we have a nitrogen to nitrogen connection that happens between these two nitrogens. In the mirror image, that nitrogen is now sort of connected to the back nitrogen, which means that when you take these mirror images and you switch it around, those two nitrogens are never going to line up correctly because there's actually sort of a different bond that's sort of formed within that mirror image. All the other ones are pretty much identical, but that one is always going to make sure that as you rotate it, something's just not going to fit perfectly. Something's going to be off because we kind of made a different connection in that mirror image that wasn't there originally. Now, if we look at this guy here, on this one here, they are superimposable, sometimes referred to as being achiral, which is a mirror image that will superimpose. So when we do the reflections here on the first one on the left, we get exactly the same sort of connections that happen. And we don't get that sort of connection where, you know, we kind of mess it up and we pull this guy out, we'll have no problem basically putting that on there. Once again, when we reflect this one, we're going to get that connection here. That's going to sort of mess up the connection that normally was here, and it's going to make them not going to be able to superimpose on each other. So a lot of times the cis guy will sort of have that situation where as it gets reflected, something will be slightly off in the mirror image that as you pull it out, you won't be able to really sort of move it around. So enantiomers are two molecules that they're mirror images of each other that are non-superimposable. So those are chiral molecules. And sometimes you can have two guys where only one of those objects, for example, in medicine works really well and the other one doesn't do anything else, as they are sort of isomers of each other. And sometimes one has different properties than the other because of the different connections that occur as you have that mirror image. Any questions on isomers? We're obviously not going to go super deep into isomers, but sort of the touching part of that there. So let's talk a little bit about electrons and complex ions and what happens with electrons in this. So the formation of hybrid orbitals to share electrons, remember hybrid orbitals, sp, sp2, sp3, sp3d, and so forth. The Vesper model does not work very well for complex ions. So when we talk about sort of complex ions, as we've been talking, really, it's about those ligands and the donating of electrons. So we oftentimes will look more at complex ions in sort of a Lewis acid base situation, where we have the electrons being donated and accepted by the sort of electron deficient metal that's in the middle. The hybrid orbitals are used by metals, depends on the number of ligands that are attached to it. So here we have sp3d2. That is a coordination number of 6. Again, if you think about Vesper, you could kind of tie it to it. 6 electron pairs is our octahedral, right? And again, that would be a hybridization sp3d2. By the way, if you just count the letters, that gives you 6, right? And that is basically 6 electron pairs, right? That's the easy way to do hybridization. So other common ones that we see is some coordination numbers here of 4. which is our tetrahedral, right? And tetrahedral is sp3. Also sp3d as well, and our sp, which is 2 letters, which is a coordination number of 2, are linear. Yeah. So certain geometries sort of apply to complex ions based on the number of ligands and really the coordination number that we see. And typically, if we have a coordination number of 2, you usually will get a linear sort of geometry. If you have a coordination number of 4, you could end up with a tetrahedral or the square planar geometry. And if you have a coordination number 6, typically you're going to be going with the octahedral sort of arrangement. So usually SP, SP3, and SP3D2 happening there. Now, when we're talking about our complex ions, since a lot of times the metal is a transition metal, those are our d orbitals, right? Where our transition metals start, as we talked about previously. There are 5 different d orbitals, which is pictured here. In the absence of any ligand being present, all of those d orbitals are exactly the same in energy. All those d subshell, basically, all the orbitals will be exactly the same energy. But when we actually do add some ligands in there, there's actually a splitting that happens of these 5d orbitals. And this is what is sometimes referred to as crystal field splitting. So what we're looking at here is actually the octahedral coordination number of 6 sort of situation happening. And what happens is we get these 3 d orbitals in a lower energy situation. These 2 d orbitals are going to be in a higher energy situation. And that's important because when electrons go into the atom, they go in which way? They go lowest energy to highest energy, right? They also, when they go into a subshell or sublevel where there's multiple orbitals, like within a d subshell, they go in one at a time, right? And then they come back and start pairing up. So when we have these ligands attached to these transition metals in this situation, we will get the splitting of these 5d orbitals. And what it affects is, in certain cases, as the electrons will fill these d orbitals, now normally the next one would go to our next orbital here, right? And what happens is, in some cases, the splitting here is not going to be so large in energy. So they will fill the orbitals like normal and just kind of go back through. If you have a relatively small splitting in terms of the energy difference. Now, in certain cases, though, when you go to do this, as the electrons are filling, they're going to go, that is like way too big. That's a really large amount of energy difference between those orbitals. So instead of the next electron going up, is going to go, I'd much rather just start pairing off down here first till I have no choice and then come up this way. So what it affects is how the electrons are really distributed in the d orbitals within a transition metal when a ligand is attached. And based on the energy difference between kind of the lower d orbitals and the higher d orbitals will result in either paired up electrons, right, or unpaired electrons, right? And the more unpaired electrons we have, we get a compound that's known as having high spin, as electrons have spin, right? The spin quantum number. And when we have more paired up electrons, they have a lower spin sort of situation. So when we do this, we can energize the different d orbitals and promote electrons upward in energy by using an equation here, which is our E is equal to H times our frequency, the throwback equation. That's a little Planck's constant, right? 6.63 times 10 to the minus 34 joules times seconds. That is not V, right? That's new. That's a frequency, right? And frequency is usually reciprocal seconds are a hertz. And that is our energy. And in the terms of crystal field splitting, we could use this equation to calculate the energy difference between the lower energy d orbitals and the higher energy d orbitals. Dare I throw out some more old school stuff here, right? That's a little speed of light is equal to the wavelength times the frequency. So that's the speed of light. I go with 3 times 10 to the 8 meters per second. Is that what most people use? Anybody had to remember 2.9979 times 10 to the 8? No? That's good. All right. That's the wavelength. I'm just taking a survey. It's okay. It's my personal survey. It's all right. So that's our wavelength in meters and obviously our frequency there in reciprocal seconds. The reason I put that there is because if we solve for the frequency, it's the c divided by the wavelength, which means we could go into this equation. And if you know the wavelength, you figure out the energy difference between the orbitals. And obviously, if you know the frequency, you could also figure out the energy difference between those orbitals. Any questions on that there? So to see how this works, since I think it's worked out for you, so we'll just talk it through here and see how we get there. So here we want to know the maximum absorption for a complex ion occurs at 470 nanometers. This is the same idea as to when we use our spectroscope, right? Or whatever they call that thing. The little graph there, the highest wavelength, right? And we want the maximum absorbance so that all of our values fall right on the scale and not off the scale. Occurs at 470. What is the color of the complex ion and what is the crystal field splitting? So first off, the color that is absorbed is the complementary color, right, to the color that we actually see. So if this guy is absorbing in the 470 region there, that means that complementary to it, the color of the solution is orange, which is why when we had did we have red solutions? I don't know what color solutions we had. We had yellow, I think, at the beginning. Or yellow ones, we picked a wavelength that was not in the yellow region, right? When you try to pick your maximum absorbance. So because of that, we can convert our 470 nanometers into meters. And by the way, nano is 10 to the minus 9, right? And that is what this is down here, converting it into meters. And going into our equation, since we have the wavelength, h is our Planck's constant, that is our speed of light, and we get 4.23 times 10 to the minus 19 joules. That's the change in energy or the crystal field splitting between the d orbitals with this energy coming off. That, by the way, is actually per atom. Yeah. So if we want it per mole, that is why our friend Avogadro's number came into play here to convert it from atoms to moles. And then we get something like 255 kilojoules per mole is the energy difference between those different d orbitals. Question on that calculation there. All right, let's lay it up here.